Hi class, I'm back again on uploading video lectures. No, uh, as you can see, I'm recording this from my laptop, no, instead of my phone, no, since I want, aside from wanting to avoid the errors I encountered on my previous videos, no, I want to, as much as possible, uh, make videos as quick, no, and as many, and at the same time, no, as better as possible, no. So kasi we all know na how really difficult it is to make video lectures, no, but for the sake of flexibility, no, uh, also to promote self-paced learning, no, I have to somewhat make a sacrifice, no. So for today, no, we're going to somewhat leave behind yung bearing capacity, no? Not necessarily leave behind kasi we're still going to need it on this topic, pero somewhat we're moving on to designing, no, shallow foundations, no. So we're going to be specific, we're going to be more specific on uh, spread footings, no, or na yung tinatawag natin na isolated footing, no. So uh, discussing discussing design of spread or isolated footings, no, we're going to divide it into several videos, no, according to uh, how are they being accomplished, no. So according to process, no, instead of doing the one sample problem to another, no. Kasi we all know, we are all aware na solving design problems are much longer, no. So just like that, no. So so don't forget, no, if you have any questions, no, kindly you can approach me, no, message me on Blackboard, no, and some of you are aware naman of my social media accounts, no, and so I'm leaving that open, no, mm, for consultation, no, and also part of the preparation, no. So I want you to secure, no, a copy of the lectures 1 and 2 set of slides, no, that I uploaded on the Blackboard, no. So although I'm going to show it later on, no, much better if you have your own copy. And also, no, before the sus- before the enhanced community quarantine, no, 'di ba, uh, I ask you to secure also a photocopy of parts of the NSCP or the National Structural Code of the Philippines 2015, no. So if you have a physical copy of this one, no, you you must you try to uh, have it as we try to have it, or uh, prepare nyo, no, as we go through the problems, no. So some sections dito, no, we're going to go through, no? And also, no, my goal after after doing after we go through this, no, ang isa ring goal ko is to make you aware kung saang part of the code, no, or which codes are to look at, no, when solving uh, when designing or also when analyzing, no, kasi uh, we can no, so we common common mistakes, no, of some students, no, kapag design problems, no, they memorize the process pero hindi nila alam kung saan nila titignan sa code yon, no. So expect na I will also teach you saang part ng NSCP yung yung ganito ganyan, no, when solving the problem, no. Okay, so uh, no more with with no more further ado, no, let's start solving the problem, no. But first, let me give you for the some basic concepts, no, of spread footings, no, and siguro shallow foundations na din. Okay. So consider this slide, no. This is from your lecture 1, no. So we all know that shallow foundations, no, uh, are foundations na wherein ang depth niya, no, are usually less than the its dimension, no. So as you can see, no, looking at this, no, I'm going to box it here, no. The ratio between the depth, no, over its dimension, no, b, are usually less than or equal to 1, no. So when we say depth, no, we are measuring, no, uh, from the top of your soil, no, up to the base of your foundation, no. Okay, no. So shallow foundations, no, are divided into three different groups, no. First are the spread footings or the wall footings, no. Next, combined footings and mat foundations, no. So for spread footings, no, they usually support, no, individual columns or walls, no, single columns or single walls, no. Combined footings, they usually support, no, two up to four columns, no, which are somewhat close to each other, no. So this one. Okay, and mat footing, no, mat footings or mat foundations are supports, no, uh, columns that are many as possible, no. So we usually consider spread footings, no, for uh, soils, no, which had high amount of bearing capacity, no, since our goal also is to uh, since our goal is to uh, since ang goal natin is to reduce, no, uh, aside from reducing the settlement, no, so we are trying our best, no, to make sure that the soil, no, will not fail, no, once we apply a certain load, no. So usually they are being used on single stratum, no. So firm layer over soft layer or soft layer over firm layer, no. So we usually consider spread footings, no, uh, if uh, your soil is strong enough, no. So uh, the soil is sufficient itself, no. The soil itself is somewhat sufficient to hold the load, no. And also this is for combined footings, no, they are somewhat similar to spread footings, except if your space is only limited, no. So mat foundations, no. So mat foundations are uh, can be suggested, no, uh, if your soil, no, if somewhat your soil is not strong enough to support a spread or combined footing, no, but you are aside from the fact na you are trying to uh, let me rephrase that, no. So let's say na you have a big area for a structure, no, pero the design load is really not that large, no. And of course, you we all know that deep foundations are expensive in nature, no. So as much as possible, we so uh, instead of suggesting deep foundation, no, we usually try mat foundations, no. Kapag malaki malaki naman yung area, no, and at the same time maliit naman, no. So ganun ang ginagawa, no, mat foundations. Okay. So this one. Okay, let me show you, no, how the spread footings look like, no, since we are going to focus our discussion uh, on spread footings. Okay, no? So spread footings have three basic types, no? So first are the square shaped spread footing, no? So the cross section somewhat square, no? And next, the rectangular spread footing, somewhat the same as the square spread footing, except for the fact that of course it is rectangular. And then next is the wall footing, no. So this uh wall footing, no, uh somewhat long, no, and it supports structural walls, no. Okay, no. So on our next videos, we are going to design uh, square spread footings, rectangular spread footing, and wall footing. Okay. So considering this slide, no, so let's go back, no, on what do we need to consider, no, when designing foundation, no. So here are the common failures that happen on foundation, no. So first is the settlement, no. So downward movement of the foundation due to consolidation and must be within the acceptable limit. no? So we already discussed this during the topic about compressibility, no, na we do, no, in order to reduce the settlement, no, is to also reduce, no, the possible increase in stress of soil, no, due to loads, no, by of course uh, setting the depth, no, setting an acceptable depth of our shallow foundation, no. Pero of course, we are informed naman na ang para masabi natin na shallow yung foundation, kailangan ang depth niya is of course hanggang dun lang sa projected dimension. Okay? Next, the heave, no? Upward movement because of swelling, no? So usually due to expansive soil or unequal overburden pressure, no? So this is also a form of uh, sl- uh, this is a form of uh, somewhat a form of bearing capacity failure, no. Pero and this is also one of the failures that we need to avoid, no, by designing designing the foundation the right way, no. So next, tilting, no. So a rotational movement that often happens to tall or slender buildings such as chimneys, silos, and water tank, no. Uh, Next, lateral movement, no, occurs in many structures subjected to lateral forces such as wind, earthquakes, and soils. Vibration, no, occurs in foundations supporting large machinery and must also avoid resonance, no. Next, durability, no, this is due to hostile and unpredictable soils, nature of soils, no. So uh, this is somewhat a concern on our how do we do your concrete mix, no. Okay, no, and we are going to incorporate, no, these common foundation failures, no, uh, to uh, the factors, no, what are the factors for a good design of shallow foundations, no, particularly on this next set of lecture videos, no, spread footings, no. So how are we can also tell that we can say that our design is good, no, if our foundation had an adequate depth, no. So the foundation must have an adequate depth to prevent frost damage. For such foundations such as bridge, piers, the depth of the foundation must be sufficient to prevent undermining by scar, no. So we need to take note of these sections from your NSCP, no. We're going to look for these sections later, no. How are we going to decide on the depth of your footing? Next, bearing capacity failure, no. The foundation must be safe against a bearing capacity failure, no. So diniscuss natin a while ago during the previous videos about ultimate bearing capacity, no. We are trying to uh, of course increase the area of our footing para mabawasan din yung bearing stress na nangyayari dun sa soil natin. no? Okay, no? So we have allowable values from NSCP 2050 regarding the allowable bearing capacity. Uh, Next, settlement. The foundation must not settle, no, to such an extent that it damages the structure. No, so this is what I already said before. Okay. Next, quality. No, so we need to make sure also that our concrete or foundation, our foundation, no, regardless of how it's made of, no, must be of adequate quality, that it is not subjected to deterioration such as sulfate attack for concretes or rust, no, pagka-steel, no. So we have covered it already, no, on your construction material subject. Next, adequate strength, no. The foundation we design with sufficient strength that it does not fracture or break apart under the applied superstructure loads. The foundation must also be properly constructed in conformance with the design specifications. No, so we have of uh, set of processes, no. We are going to check, no. We are going to check if our foundation can be able to withstand, no, certain type of uh, loads, no, and failures, no. So from the NSCP 2015, we are going to look at these sections. Next, also the same with this one. Next, we have to consider adverse soil changes. No, so the foundation must be able to resist long-term adverse soil changes. An example is an expansive soil, which could expand or shrink, causing movement of the foundation and damage to the structure. No, so uh, we also need to consider the unpredictability of the soil when designing foundation. Next, seismic forces. The foundation must be able to support the structure during an earthquake without excessive settlement or lateral movement. No, so uh, look at the let's let's discuss, no, the set of the processes that we need to on how are we going to solve for uh, how are we going to design, no. So first we are to decide, no, uh, we are to decide, no, on the dimensions of your footing, dimensions of your footing, no? So uh, we are to approximate first the thickness, no, and then we are going to determine, no, the required or the minimum cross section, no. So for of your footing, no. So next we are going to check, no, we are going to check, no, so we are going to check, no, the adequacy of your footing against first the one way shear, or this is also known as beam shear. Next, we are to check if your design footing is adequate against two-way shear. or also known as punching shear. Next, we are to check uh, if your uh, footing can withstand moment, no? And at the same time, we are to determine how much reinforcement should we place on that footing of reinforcement. Next, we are to check if uh, our footing, if rather, if our reinforcement is within the required development length. Last but not the least, we are also to check if uh, our footing can also withstand, no? So can also withstand bearing stress. So let's if your footing can withstand bearing stress, no, from your concrete column or your wall, no? So let's go back, no? So first, so dimensions, no? Thickness multiplied by area. Next, one-way shear or beam shear. Next, two-way shear or punching shear. Next, check if it's also adequate with movement, no, and design reinforcement. Next, we check the development length. Last but not the least, we check if it's adequate against bearing stress from concrete column or from uh, column or wall. Okay, so basically, we're going to have minimum siguro of 6 videos, no, regarding uh, concerning design of spread footings, no, and we are going to solve 3 problems simultaneously. First, isolated or spread square footing, isolated or spread rectangular footing, and wall footing, no? Or strip footing. Okay, so let's read some, uh, or rather, let's solve some example. So consider this problem, no? This is a problem concerning the design of an isolated, no, or spread square footing, no? So a square column is to support a 500 millimeter square column, no, that carries service dead load of 1,200 kilonewton and a service live load of 1,120 kilonewton. The column is reinforced with 8 25 mm diameter bar. The base of the footing is 1.5 meter below the natural grade, where the allowable soil pressure is 310 kilopascal. The soil above the footing has a unit weight of 15.6 kilonewton per meter cube. Assume that your Fy, no, or this what you call the yield strength of reinforcing steel, is equal to 275 megapascal. F prime of C, or the 28-day compressive strength of concrete, is equal to 27.5 megapascal, and the unit weight of concrete as 23.5 kilonewton per meter cube. Design the footing using 2015 NSCP. No? So let's look at this uh, problem. No? Okay. No? So this one. Okay. So there's your footing. No? So this is your footing now. No? So consider this footing. No? Subjected to load P. No? Combination of dead load of 1,200 kilonewton and live load of 1,120 kilonewton. No? So the depth, no, from the top of the soil up to the base of the footing is 1.5 meters. Your allowable bearing capacity is 310 kilopascal. No? Your F prime of C, or the strength of concrete, 27.5, Fy 275. No? Unit weight of soil 15.6 kilonewton per meter cube. No? Uh, and unit weight of concrete is 23.5 kilopascal. No, not kilopascal. So this is kilonewton per meter cube. No, dapat. Okay. No, so that's that. Okay. No, so first, we need to approximate. No, we need to get. Uh, we shall assume, no, the thickness of your footing. No, so as you can see, no, many references and practices have presented uh, formula, no, on how are we going to assume the thickness of our footing. Pero uh, what I'm going to this wala namang mali doon, no? There's nothing wrong with that. But let me show you first, no? If we assume, no, what will happen if we are going to assume, no, the minimum value first, no? So okay, so consider this uh, figure, no? So this is how our footing looks like, no? So we have a we are going we are going to put reinforcement, no, on the lower part of your footing, no, and you know, um, as you all know, no, uh, we are no, so we are going to put reinforcement, no, on the lower part of your footing. Pero how are we going to decide, no, kung saan banda sa footing, no? So let's look at our codes, no? So on our code, no? Okay? So on our codes, Okay, on our codes, let me show you that. Okay, so from our code, no, the minimum thickness of our footing, no, is somewhat dependent on the number of floors of our building. No? So if it's one story, the minimum thickness is 150 mm. No? If it's two story, the minimum thickness is 175. No? And if it's three story, no, minimum is 200 millimeter. No? But what if, no, since we are going to be specific about since we are going to design specifically reinforced concrete footing, no? So let's look on section 4. Okay? No, so from the section 4, no, considering reading section 413.3.1.2, no, overall depth of the foundation shall be selected such that the effective depth of foundation reinforcement is at least 150 millimeter. Okay? No, so let's take note of that. No? Okay? So uh, let's go back from our original notes. Okay, no? So as you can see here, no, the effective depth, no, the effective depth na tinutukoy doon, no, is the measure of the distance from the top of your footing, no? So top of your footing, no, up to the center of your reinforcement. Okay, no? So we have two choices, no? First, kasi nga o nga pala, you have to consider na ah, we are to reinforce two sides of your footing, no? So this is just the section, no? Kapag top view 'yan, no? It is a square shape, no? So magkapatong yung reinforcement, no? Since in real life naman, hindi naman natin pwedeng putulin yung reinforcement, no? So ah we have two choices. No, what are we going to do? No, first, we considered your minimum effective depth of 150 from top of the foot up to the center of the top bar. No, or next, the 150 mm is from the top of your footing up to the center of your bottom bar. No, so next, so what is that 75 millimeter? No, that is from section 420.6.131 of your NSCP, no, regarding the minimum concrete cover. You try to look at that, no? So therefore, we have two choices, no? So pero ano ang pipiliin natin, no? So yung nakikita nyo dito na 1.5 diameter of bar, no, is the measure from the center of the bar, no, up to the face of the reinforcement, no. So that is what, kasi nga this is half of the diameter, no, plus the whole diameter, no, that is 1.5, no. So yung 0.5 naman dito, no, dahil sa ilalim yung kinonsider natin, no, it's just the half of the diameter, no. So therefore we have two choices. How are we going to decide for that minimum thickness of our footing, no? So yung inassume natin thickness, no. First, if we consider the top bar, no, that's equal to 150 plus 75 plus 1.5 multiplied by the diameter of bar, no. So from the calculator, we we arrive at the answer 262.5 mm. no? Pero the red marking here, no? So we rounded it up, no? Rounded up kasi nga we are talking about the minimum thickness here, no? So we are going to round it up to the nearest 25 meter, no? It depends on you, pero for the sake of our discussion, no, ni-round up ko siya on the nearest 25 mm. So ang pinakamalapit sa kanya is 275 millimeter, no? If top bar is considered as the minimum uh, effective depth. Next, kung bottom bar naman, no, 150 plus 75 plus 0.5 multiplied by 25. That is equal to 237.5, no, rounded up to the nearest 25 mm, that is equal to 250 mm. Okay? No? So, ngayon, ano ang pipiliin natin dito, no? So, we can check both, no? So, ang gagawin ko, magko-consider ako ng isa sa dalawang 'to. So, you can just check kung the process will just be the same, pero it's up to you what are you going to check. Okay? No? So, next, no? So, next thing that we need to do now, no? Meron na tayong thickness. So, therefore, we proceed with approximating the design of your footing. Let's go back to the NSCP. Okay. No? So, for this is written from section 413.3.1.1. No? So, the minimum this area foundation shall be calculated from unfactored forces and moments transmitted by fission to soil or rock and permissible bearing pressure selected through principles of soil and rock mechanics. No, so we are to apply, no, yung natutunan natin from our bearing capacity in approximating the base area of our foundation, no? So going back again to the table, no, rather to the lecture notes, no, that we have, no. Okay, we have what we call the effective bearing capacity, no. So what are we going to do? We are to reduce the since meron tayong allowable bearing capacity, no, babawasan natin siya ng gamma H from your soil and gamma H from your concrete, no, and that will be equal to the service load, no, service load over the area of your footing, no. So your Q effective or the effective bearing capacity, no, is equal to 310 yung given minus 15.6 multiplied by 1.5 the depth of your footing minus 0.25. So ang kinonsider ko dito is that 250 mm, no. So you might want to check kung ganito din ba yung magiging sagot if we consider the 275 mm minus 23.5, no, the unit weight of concrete multiplied by 0.25, no, that is your effective bearing capacity, no. Lumabas dyan is 284.625, no. This is equal to the sum of the dead load and the live load, no. So saan ko nakuha ito? DL plus LL, no. Let's go back again to our NSCP again, no. So going back to the NSCP, no. Going back to the NSCP, no. So we have what you call the unfactored loads, no. So basic load combinations where allowable stress or allowable strength design is used. structures and all portions thereof shall resist the most critical effects resulting from the following combination of loads. No? So D plus F, D plus H plus F. No? So we have set of formulas here, pero meron tayong given na dead load only tsaka live load only. So ang gagawin natin dito, we are to eliminate everything except for dead load and live load. So we eliminate this one, eliminate, wala na to, eliminate this one, eliminate, eliminate, and eliminate. So, ang matitira na lang dead load at live load. So, pag tinanggal natin yung other loads dito, matitira is only the dead load, D. This one, D plus L. This one, D ulit. This one, D plus 0.75 L. No, this one is equal to D ulit. So, the maximum, no, maximum load maximum unfactored load or maximum service load that we can use is the sum of the dead load and the live load. So that is D plus L. Okay, let's go back to the notes again. That is how we arrive at the sum of 1,200 plus 1,120. So this one. Over the area of your footing, no, this is equal to the B base squared. No? So 285.625. This is your effective bearing capacity. No? Kaya effective, no? Meaning since bearing failure, no, will start on the bottom of your footing na kung saan may interface ang footing mo tsaka yung soil mo, no? Doon magsisimula yung bearing capacity failure. So tinanggal ko lang yung soil tsaka yung concrete, no, from the computation of the depth. No, so 184.625 is equal to 1,200 plus 1,120 over B squared, no? So solving for B, we have 2.86 meters, no? So we round it up naman on the nearest 100 mm, no, or 0.1 meter, which is equal to 2.90. Okay, so may possibility na different siya kapag ginamit natin yung 275 mm. Pero ito yung value kapag ginamit natin yung 250 millimeter. So next, no, we are to compute naman yung ultimate bearing stress natin, no, between the soil and your footing, no. So Q alt is equal to the factored load naman, no, over the area of your footing, no. So that is equal to factored load over area of footing, no, is equal to 1.2, no, multiplied by the dead load plus 1.6 live load, no, over yung computed area natin, which is equal to 290 squared, no. So this is written from section 203.3.1, no, regarding factored loads. Okay, so let me show you again, no, that, no? So this is basic load combination for strength design or load and resistance factor design, no. Okay, so dito siya nanggaling, no. If we remove all the loads except for the dead load and the live load, no, so x natin yung F, x yung T, x, no. So ang matitira lang 1.2 dead load plus 1.6 live load. Okay? No? So let's go back again to our notes. O nga pala, don't forget, I also uploaded these notes on your blackboard. So you can see, you can be able to have your copy. So this is equal to 1.2 multiplied by 1,200 plus 1.6 multiplied by 1,120 over 2.9 squared. No, so we will arrive at the answer 384.305 kilopascal. No? So ano ang kinaiba nito sa Q allowable natin? No? So this is somewhat different from our ultimate bearing capacity. No? Kasi ito yung parang actual na design natin. No? So iba pa yung kapag nag-bearing pag ginamit natin yung K-Terzaghi. Why? No? So look at this section of our paper. No? So yung the one written in red ink. No? So we know na yung ultimate Q ult from Terzaghi, no? If we divide it by a certain factor of safety, lalabas yung ating Q allowable or the allowable bearing capacity. No? Yung Q allowable na yun yung given natin kanina. And we can assume na ang Q ult natin is yung factor of safety natin na which is 3 multiplied by 310, no? This is 930. So therefore, actual, no, pag nag-design tayo, safe pa siya. Okay? No? So might as well do check, no, kapag ginamit natin yung 275 millimeter na thickness, no? Do your own check, no, regarding that matter. So we're going to proceed with it. On the next video, but let me do the same first on our other example. So let's consider this next problem, no? Sample problem 2. You're given a footing, no, that supports a 600 millimeter square column, no, with actual dead load of 1,680 kilonewton and actual live load of 1,350 kilonewton. So 1,680, 1,350. The depth of the footing is 1.80 meters from the ground, and the allowable soil pressure is 230 kilopascal. Unit weight of soil is 16 kilonewton per meter cube. Unit weight of concrete is 24 kilonewton per meter cube. F prime of C is 28 megapascal, or the 28-day compressive strength of concrete, and the Fy is equal to 345 megapascal. Design the footing using NSCP 2015 if its width is limited to 3.20 meters. No? So the difference between the isolated square and isolated rectangular are the dimension. No? And usually, kapag ang ang column load natin masyadong malaki, no? And may cases na ang lote natin had a certain limit, no? Or yung lot natin is limited, and yung column placement natin, no, kapag masyado nang malaki ang load, no, hindi niya kakanin yung no? So let me rephrase that, no. Let's say we're going to we are going to apply the same principle, but we're going to design a square footing, no. We are able to know na the width no, or the dimension of that square footing is very large, no. So therefore, in order to avoid that, no, so usually instead of square, no, we usually do isolated rectangular footing, no. So best example niyan yung kapag uh, pag may setback tayo, no, and we usually cannot violate the property line, no, kasi minsan yung kung minsan yung katabi nating lote merong foundation, and as foundation engineers, no, hindi natin pwedeng galawin na kung ano yung nakatayo na, no, and we can only build something, no, within our property, no. So let's solve this problem, no, on the same manner as what we've solved earlier, no. So let me show that to you, no. So you're given a we sketch it the same manner as earlier, no. Pero, no, so here it is, no, and we are going to approximate, no, first the depth of your footing, no. So the same process kanina, kaso ang ginawa ko na, no, I decided to assume na minimum natin is 150, no, 150 mm considering the top bar, no. So from the top of the footing up to the top bar, no, the center of the top bar. So therefore 150 mm plus 75 mm concrete cover plus 1.5, now multiplied by the diameter of to be used multiplied by 25 mm, which is equal to 262.5 mm. And we are going to use 275 millimeter, no, rounding off to the nearest 25 millimeter. So this is it. Next, we approximate the dimension by computing the uh, effective bearing capacity, no. So same process lang nito nung kanina, no. So might as well try to read the code, no. Try to take note of the codes na I gave before, no. This is equal to 230, no, multiply minus 15.6 times 1.8 over minus 0.275 minus 24 times to 0.275, no. So minus gamma h of soil minus gamma h of concrete, which is this is equal to 199.61 kilopascal, no. Your 199.61 is equal to the service load over the area of footing, no. Dahil given natin ay dead load and live load only, no, we do it the same manner as before. 1,680 plus 1,350 over 3.20 multiplied by b, no. So as you can see here, no, it said na one of the dimensions should be 3.20 meter. Kaya we are going to consider it on the computation, no. So we will be able to solve for b, no. This is equal to 4.74, no. So we round it up on the nearest 100 millimeter or 0.1 meter. This is equal to 4.8 meters. Okay, next, no, we have now your approximate dimension of footing, no. So mamaya, no, on our next set of videos, might as well try to do check, no, if swak itong mga dimensions natin, no. Okay, next, for ultimate bearing stress, no. So ultimate bearing stress, no, QU is equal to factored load over the area of footing, no. So factored load over the area of footing, which is equal to 1.2 multiplied by 1,680 plus 1.6 multiplied by 1,350 over 3.20 times 4.80. That is equal to 271.88. O nga pala, yung mga ultimate bearing stress dito, now we are going to use it when we do adequacy checks already. Okay? So, that is how you solve for uh, that is how you approximate dimension if for uh, rectangular footings. So let's try to check if we assume na this is square footing, 3.20 multiplied by 4.74, so is equal, so if we get the square root of that, uh, it's about 3.89 meter, but of course one of the dimension is only limited to 3.20 meter, probably dahil sa property line yan or what, we are going to assume that they cannot, or we cannot use square footing, so on our next set of problem, we are going to do naman wall footing or strip footing. So last but not the least example, so consider design a wall footing that carries a 250 millimeter thick wall with a service load of WDL is equal to 60 kilonewton per meter and WLL is equal to 35 kilonewton per meter. The bottom of the footing is 1.1 meter below the natural grade line, where F prime of C is equal to 21 megapascal, Fy is equal to 420 megapascal, gamma of soil is equal to 17 kilonewton per meter cube, gamma of concrete is equal to 24 kilonewton per meter cube, Q allowable is equal to 150 kilonewton per meter squared. Use temperature bars of 12 millimeter diameter and main bars of 12 millimeter diameter. So let's refer to this to our set of notes. Okay. So if you look at this notes, if you look at our set of notes, most of our given loads are in kilonewton per meter cube, indicating that it's a uniformly distributed load, So for a uniformly distributed load, we are going to consider a 1 meter strip, and then we are going to implement it, throughout the wall footing, So mag-assume lang tayo ng 1 meter strip, 1 meter strip, So this is your let's say this is your strip, and then i-implement lang natin siya, throughout the plan, so wala naman tayong given na plan, pero kung meron tayong building plans, and we tend to use or implement a wall footing as our foundation, so yung kabuuhan ng plano natin, doon tayo gagamit ng wall footing. no? So here are our given, no? So ito na yung mga given values natin. Okay? And then we approximate the thickness of our footing, no? So for the approximate thickness of footing, we just we implement the same method, no? And we assume that our we assume, no, that our mean bars, no, for consideration is on the bottom, no. So therefore this will become 150 millimeter plus 75, 150 plus 75 plus 1.5 multiplied by the diameter of the reinforcement, which is equal to 12 millimeter. No, this is equal to 243 mm, and rounding up to the nearest 25 millimeter, we use 250 millimeter. And approximate our dimension, no, so we compute the effective bearing capacity, no, is equal to 150 minus 1.7 multiplied by 1.1 minus 0.25, this one, okay, and minus 24 multiplied by 0.25. Therefore, our Q effective is equal to 129.55 kilopascal, which is equal to the service load, no, in kilonewton per meter, no. So kasi kilonewton per meter na yan because we assumed a 1 meter strip, no, over the of our footing. No, so 129.55 is equal to 60 plus 35 over B. Our B is now equal to 0.73, rounding up to the nearest 100 millimeter. No, we are able to get the value of 0.8 meter. 0.8 meters. Okay, next, no, since we already have a an approximate dimension, no, we now proceed with computing the ultimate bearing stress, no. So again, let me reiterate to you na it is somewhat different from the ultimate from Terzaghis ultimate bearing capacity. So Q ult is equal to the factored load in kilonewton per meter over the B, the base. Now this is equal to 1.2 multiplied by 60 plus 1.6 multiplied by 35 over 0.8. Our factored load is now equal to 128 kilonewton per meter, and our ultimate bearing capacity is equal to 160 kilopascal. No? Okay. So uh, that would be all, no, uh, concerning the dimension of the footing and the ultimate bearing stress, no, of both uh, isolated square footing, no, isolated rectangular footing, and wall or strip footing. So that would be all for this video. No, on our next video, we're going to start checking, no, our dimension if uh, dimensions if this uh, footing that we're able to uh, design can withstand various kinds of loads, no, such as uh, shear, no, so shear in the form of one way or two-way shear, no, and if it can withstand moment, no. So again, no, we're just going to continue uh, the problems that we started solving, no, the problems concerning isolated square footing, isolated rectangular footing, and strip footing or wall footing, no. So uh, thank you for watching, and see you on the next video.